Hello and welcome to Shenzhen I, a game where you are an engineer who has moved to Shenzhen, China to work for a technology firm there, and you develop and program various different prototypes using microcontrollers and other circuit parts. Yeah, so let's get started. One of the cool things about this game, not really cool, but one of the interesting things about this game is that a lot of it takes place outside of a game. So there's this long PDF of data sheets that you basically have to pretty much constantly reference. And you can see here, they want you to print it out and put it in a binder, which is a lot of work. I'm just going to use it out of here. You even have a nice little visa application form as you're coming into China, yeah, application notes. So basically, if you've ever done anything with electronics, you know that a lot of that is reading data sheets. The main thing that you end up using in this game is this little MC. Well, it's MC4000 is a cheap one, but and it's got this basic programming language. It's a lot like assembly. So basically you have one register. And that said, I've never actually done anything in assembly. I've only played around with it a few times. I'm not sure how close or how far this is. I'm assuming it's a little bit far, but it's the closest thing that I know to compare it to. So you can move things into registers from various pins. You can jump around in the program, you can sleep, you can do arithmetic operations on your register, and you can do comparison operations. There's no cushy language features in this, like if statements or anything crazy like that. You're going to be stuck with this small set of instructions throughout pretty much the entire game. But that's sort of the fun of it. You've got this limited palette of options and you have to figure out how to make them perform interestingly. So let's check it. Let's check this out. I'm going to start with just one of the easier ones. I've already played a lot of this game, but I want to give you sort of an introduction to like how you would play it, and then we'll move on to some of the more interesting puzzles further on. Let's start out with the replacement factory module. As you can see, most of the game takes place inside your corporate concept mail, which it makes sense because everything on in a corporation has to have some crazy name, right? They have to. It can't be mail. It has to be concept mail. Yeah, so we open that up, and this is where you get all the different assignments that they want you to work on. So this guy is telling us our factory floor has some examples of older equipment that require signals to be amplified. Okay, so we basically just want to amplify this. We had a device to adjust signals for this type of machine, but it was recently smashed. Okay, so we'll open this up in Concept CAD, which is the name of the design software that they have. And you can see sort of a leaderboard of how few lines of code someone has been able to write this in and how little cost they've been able to do it with. And we'll create a new design. We'll open this up. So you start out with this blank board, which basically just has your inputs and your outputs. Well, you have your list of parts over here that you can drop in. And it tells you what you're basically supposed to do. Control in is a simple input that's connected to factory equipment. The control out is a simple output connected to other factory equipment. And the signal from control in should be multiplied by 2 and copied to control out. Okay, simple. So the way that you can tell if you've done this correctly is they basically have this little verification panel here. And it shows what signals it's going to give into the system and what signals it expects out. So it's sort of like unit tests or integration tests for your electronics, which is very fun. With sort of like I guess this is sort of an oscilloscope sort of view. It would be one thing I would request for the developers. It would be really fun if you could put a probe someplace and check what is this circuit output doing, because you can't monitor everything, and sometimes that becomes irritating, but let's ignore that for now. So the part we're going to use for this is the MC4000, which is basically the bottom of line microcontroller it only supports 9 lines of code, which you can write here. There's 2 different kinds of inputs on these. There's the X bus inputs, and then there's the analog inputs and outputs that they have a P0 and P1, and you only get 2 of those. So we're going to take control in, and we're going to pipe that into P0, and take P1 and put it into the control out. So if we simulate that right now, you can see that it's sending in all these values, and the output is always 0. So what we want to do is reset, and then we want to read in this value into our ACC register. So we will move P0, which is right there, into ACC. And now if we run it, you can see ACC is sort of, well, one of the things you have to do in this game is remember to make your microcontroller sleep. Because if you just keep it running, obviously it uses a lot more power. And for some reason, even though most of these are plugged in, if they're concerned about that, I guess it's still probably good practice. But what you'll usually want to do is have a sleep of 1 after everything you do. And you can see these time units here are 1 second or 1 unit of time. Otherwise it'll complain, and that's not fun. So we're going to simulate it again, and you can see the ACC value is jumping around with what the input is. But what we want to do is multiply that by 2, according to the information here, so we can amplify it. So let's check out the manual again and see what instructions we have that we could use for that. This is actually not the language reference. Here we go. Okay, so move, this is the one we used before. Copy the value of the first operand into the second operand. Operand? I don't know how to say that. Let's see. Arithmetic instructions. I don't know how to say anything, apparently. So here we've got add, subtract, multiply. And multiply is the one we want. So multiply is the first value by the value of the ACC register, and store the result in the ACC register. Okay, perfect. So we've moved it into the ACC register. And what we're going to do is do multiply 2. So now if we look at it, you can see the ACC register is just about twice as high as it was before. Now our last step is just to move the ACC register into the P1 output and simulate it. And there you go, you can see that it is outputting the correct information. It's verifying it. You can speed that up a little bit if you drag that. Checking all the inputs, check it out, and there we go. We have finished it. We've completed our control signal amplifier. So you can see we did it in 4 lines of code. It looks like someone managed to do it in 3. Not sure how you would do that. Power usage, production cost, yeah, we did good there. 3 lines of code, how would you do it in 3 lines? Yeah, so it's some of these you'll be left puzzling after you have completed it. Wait, how would I do this with less? Yeah, that's definitely something that will drive you insane slowly as you play this game. So be warned. So I'm not gonna go through this too much. I think we're ready to jump into some of the more advanced puzzles. So the one, let's see, that I'd gone to here, let's see, is a token-based payment kiosk. Create a working design for this product to view histograms and leaderboards. Oh wow. Okay. This machine just has to know when you've put in the right coin total. It rings a bell to let the person behind the counter know to hand you your item, and it makes a change in real physical coins. It's really like bygone times. Okay, I'll believe that. So we open it up. Ooh. So as you can see, it's a little more exciting already. We've got various things, various other components on the board. and we've got a lot more inputs and outputs. So in1, in5, and in12 are simple inputs connected to a mechanism that accepts and detects 1, 5, and 12 tokens. Bell is a simple output connected to a solenoid that rings a small bell. Okay. Out and out 5 are simple inputs connected to a mechanism that exchanges tokens as change. Oh wow. So this is going to be interesting. After a sufficient number of coins have been inserted, the payment kiosk should ring the bell and dispense change as indicated in the verification tab. The cost of the item is set by the operator using the dial that can be read as an XBus input. Okay, so this is the dial right here. So this is a 16 token item cost, I suppose. And we look at the verification tab. We can see some of the inputs that we're going to expect to be getting and the outputs that we're supposed to be getting, giving. So let's see, we've got this here in 12. Okay, so this is basically, we need to look at these and see which coins have been put in, probably, and then keep track of that. So we're going to start out with one of the more expensive microcontrollers because I'm pretty sure we're going to end up needing it. This one has 3 or 4 different XBus inputs, which I'll explain in a minute, and it also has 2 registers that we can store information in, which is very helpful. Let's see here. So another part we're probably going to want to use, because we still only have 2 actual inputs. Any of these inputs that are just simple can't be connected to XBus inputs. So you get pin mismatched. Can't connect it to that one. You have to connect it to a P-type input, which is sort of problematic. But thankfully, we have a bus expander that we can use. This is a, let's see, this one right here, the DX300 Digital I/O Expander. Ooh, fun. This can be used for inputs and outputs. You get 3 of these pins, but you can read. The limitation of this is these are not analog pins, these are digital pins. So you get a 1 or 0 value. That's all you get. You can't read like something in the middle. And it translates it into 1 XBus output. I don't know why they have 3 here. So far I haven't found it to be useful. It basically just takes all this information and sends it over a bus. So let's take a look at that. We'll drag this guy in here. This is $1, not dollar, but I'm not going to attempt to say the correct word for the Chinese currency here. And we're going to take in 1, put it into P0, in 5, put it into P1, and 12, and put it into P2. So now we're going to take all of this, I'm going to move it over onto our X0 input. So if we look at the documentation for this, it's going to take all of these, and what it's going to give us on our XBus is something like this. So if P0 is 0, and P1 is 0, and P2 is on, it's going to say 1, 0, 0 to show that it seems to start backwards. So it's showing P2 first. So P2, P1, P0, as you can see, only the last one is on. Yeah, so it communicates that with a 3-digit number. Yeah, so we move this into the accumulator. And one of the things about XBuses, they're a little confusing. I don't 100% understand them so far. But you have to, they're basically blocking and non-blocking. So I feel like this is probably a pretty unrealistic part of the game. I don't think, well, I mean, I haven't really done a lot with communications protocols and microcontrollers, so I don't really know. But basically, it will wait until you read it. I'm trying to find where it talks about them. XBus. XBus values are discrete data packets from -999 to 999 inclusive. XBus pins are marked with a yellow dot. XBus is commonly used to send data between microcontrollers. Okay, yeah. Simple I/O pins can be read and written at any time with no regard to the state of the connected devices. XBus, however, is a synchronized protocol. data over XBus pins is only transferred when there's both a reader attempting to read and a writer attempting to write. If a read or a write is attempted without a corresponding operation on a connected device, the operation will block. So I'm not really sure how that would actually work in an electronic sense, but in the game, basically, if it's sending something, you have to read it. This one here, I think, will just let you read it in a time. I don't think it cares, but if you're using other microcontrollers, it's going to freak out. So what we'll do is we'll move it to the accumulator and we'll save it. So you can see it's sending in values right there. And I think the first thing we want to do is start to keep track of how much money they've put in. So, because I think we need to know that. Is a simple, it rings a small bell when triggered. After a sufficient number of coins have been inserted, it rings the bell and dispenses change. Okay. So instead of, it is important with some of these to move it to a register because you can only read it once. Again, this particular part, this DX300, allows you to just continuously read it. So we're going to take advantage of it. So we need to use a test operation, which is sort of like the if statement of this. Basically, we've got all these here. Test instructions T, EQ, test if a value of a first is equal to the value of a second. And another thing that they sort of threw in here, I don't think this is actually a feature of assembly languages. I think it would all be jumps. But maybe I'm incorrect. Correct me in the comments if I'm wrong here. They have this idea of conditional statements. So whenever you use a test operation, you're actually going to have any line that comes after that. If you have a plus, it's going to run, and if you have a negative, it's going to not run. So it's basically enabled and disabled by the test instructions. So I mean that sort of makes sense. Again, I think that's probably just sort of to make it easier for you. So we're gonna give that a try. We're going to use TEQ X0. So we're comparing that, and we want to see. Let's start out by looking for 12. So if you remember, the number it's sending is like backwards. So if we step through this, which I think we can do. I'm going to say 100 for 100 for now. You can sort of step through it's sending data. So you can see it sends something there, but yeah, so it's reading it. Let's advance an entire time step. Oh, it's not sleeping. We have to sleep. Sleep is important. Okay. So we get to here, and we see this value is on as we're testing it. We jump over. Okay. I guess this doesn't, that's the other thing I would like if it showed the values going over the bus a little more clearly. But basically, we know that we're expecting to get a, when this is on, we should expect to get 1, 0, 0, because it's P2, P1, and P0. So we're checking that, and if that is the case, what we want to do is add 12, because this is, they put a 12 coin in. We want to add 12 to the accumulator. So let's give that a try. I'm going to simulate it, and it looks like you can see the accumulator going up, and they put in, over the entire simulation, up to 60 coins apparently, so that's nice. And now we basically just have to do the same thing for the other coins. So we'll test for 0, 1, 0, because we're checking if 5 is on, and that's the middle one. So off, on, off. And we'll put the plus to say we only want this instruction to run if the test operation before it ran was successful or evaluated to true, I guess. And we'll add 5. And then the last one, we want to check if it is 0, 0, 1, which means this 1 is on. And if that's the case, we want to add 1. So now as we run through it, you can see the accumulator going up all the way to 83, which we'll assume is how much money they ended up putting in this machine. So the next part part of this is ringing the bell when they've put in enough money. So this isn't too hard. What we want to do here, we've been keeping track of how much money they've put in using this accumulator here. So we want to see, equals isn't going to work because they might not put in the exact same amount, the exact correct amount. They definitely won't because we need to give them change. So what we want to do instead is TGT, which is greater than. So test if it's greater than the accumulator here. If it's greater than the price, so this is the other thing, we need to actually read in what the price is. And I think the easiest way to do that is just to drop this in here. This is an XBus value, and we'll connect it to this XBus. You can press tab to see how the wires are connected, because when they get close, it's difficult to read the labels. You can't see that this is X1 here. So we want to compare it to X1. So if accumulator is greater than X1, then we want to ring the bell. And the bell is just a simple output. So we'll connect our P1, which is a basic analog output, to it. And we'll turn on the bell. What's it expecting? Just to stay on for a few seconds? I'll have to figure out how to turn it off, but we'll test with this for right now. So we'll move 100 over to P1, and let's give it a test. So we're just gonna step through it one at a time here. You can see they put in a 12, we're waiting for 16, and then they put in another 12, and we got to 24, and it's sending out that bell signal, as you can see right here. We'll keep stepping through it. Okay, so our problem right now is it never puts out change. You can see here it was supposed to give them a 5 and 3 ones, and it never, let's see here, it never turns off a bell. So it looks like the bell is supposed to only turn on, ring the bell, and dispense change. It looks like it's only supposed to stay on for 1, 2, 3, 4 ticks. Okay, but we may want to focus on the, trying to think which one to tackle first. Let's look at the change. So we need to basically dispense change by triggering these two outputs over here. And since we only have one analog output, I think we need to grab another one of these so that we can expand our X2 bus into writing to that. So we'll connect the middle one. None of these matter, like I mentioned before. To P0 will be our 1 coin, and P1 will be our 5 coin. So what I'm thinking, as we're running it, accumulator has how much change we've got in it, how many coins they've put in, right? And we know the price. So maybe what we should do at the end here is subtract the price, which again is X1, from the accumulator. So now if we simulate it up to here, we see accumulator goes up to 12, and then as soon as this line triggers here and we say, oh, we have enough money to pay for it, it immediately calculates how much change we should give back to them. So now we've got that stored in the accumulator. The question is, we have to have this go for multiple cycles, I think. So I wonder if we should instead copy it into that. But we then need to do like subtraction to it, so that gets kind of tricky. Because we don't want to do all these at once, as you can see here. We want to do we want to check if we can send out however much, and then we want to send that out. And if you look over here, you can see the parts that they've recommended you use and the parts they haven't. These two registers here, these are basically register expanders, so you can keep track of more data besides just ACC and DAT. So we may have to use those because those are turned on right now. Those are enabled, so they may want us to use those. But let's just see here to start with, because look, as you can see here, we're running out of code pretty quickly. Okay, sub x, so we subtract it out. You can use comments in this language, but they count as a line, so you're going to run out of lines even quicker if you use comments, which kind of sucks, but I get it. It's what they want to be able to have everything on this one little screen here. So now that we've subtracted it, I guess we want to see if it's greater than 5, right? Because we want to see if we can give them a piece. We want to see if we can give them a piece of change that's 5. And the trouble here is this is always going to run. I think what we need to do is have a little jump routine here, because as you can see, this gets complicated quickly. We're checking if it's greater than up here, and we only want to run any of this code if it was, like, if we've had enough. But as we get down here, it's going to be a problem. Let's see. So maybe what we want to do is set it into a mode. So let's see here. We subtract it, and then what if we set a mode? So basically we set dat. We call dat our we're dispensing change right now mode. So we move 1 to dat. And then on the next round, or anytime, we always check. This is going to be tricky. This is where it gets interesting, because we're running out of lines of code. We're running out. I wonder if what they want us to do is to write this into a central register that we can communicate to with different microcontrollers, and have one that's designed to send out change and one that's designed just to count up the actual value. That might be what they want us to do. Let's take a look at that part here. What is it called? It's the 200p. No, it's a 100p 14. That's the writable one. Random access memory 100p 14. 100p 14 random access memory offers yes auto increment. You won't have to waste precious registers keeping track of memory addresses. 14 random access memory cells, 2 independent auto incrementing pointers. Okay. The following example circuit reads in 3 value packets from input and writes them to the output in reverse order. Okay. So in other words, this circuit is it moves 0 into it. It moves that. So it moves all these in. And then, well, maybe this is more useful. All memory cells initialize to 0. All pointers initially point to the first memory cell. Memory pointers can be read and written over XBus with the A0 and A1 address pins. Memory values can be referenced by pointers and can be read and written over the XBus. Okay. Automatically increment to the next data location. Well, let's take a look at this bit. Yeah, so let's say, oh, yeah, I see everything. You sometimes run out of actual room on the board. Let's say we want to get rid of this part for now, and we want to instead have another little dedicated microcontroller that just gives change, essentially. And I wonder if the best way to do, I wonder if we don't even need this. So like, we could connect these with an XBus. So whenever that happens, we send this value over there. We send how much change it needs to give out over to this one. Let's give that a try. So we're going to move our accumulator value over to x2 here, and then we'll go to sleep. Over in this one, we're going to sleep until we're going to sleep X, which stands for, I'm not sure what it stands for, but it basically makes it sleep until it reads something off of an X bus. And we want to sleep until we get any data off of X0, which is the one that we've connected over to this microcontroller. Let's get rid of this part for now. Once we actually get something in, we want to move the value over to the accumulator, because once you've read a value, you can't read it again. So it's sort of important not to, like we couldn't do a comparison operator on X0, because the next time we want to look at X0, it's going to be gone. It's going to have been read off the stack. It's not going to be there anymore. So we really have to store it inside the accumulator. Actually this is backwards. Move our bus over to the accumulator. And we can test this out real quick just to see. You can see this one's running and this one's sleeping. And at this point, when it rings the bell, when it has enough money put into it, it's going to activate this microcontroller. It's going to come out of sleep, and it's going to move that value. So you can see we have how much change we should have right there, which is cool. And we're going to reset this one once we get the change over there, because we don't want it thinking it still has money in it when we have told this microcontroller, hey, give out change. We don't want it to be still counting as money. So let's connect these analog values since we can. It gets kind of interesting trying to route stuff around, but this one hasn't been too hard so far, but some of them are kind of tricky. So now we actually need to give out change. So we assume that the accumulator has the amount of money that we should be giving out in it, and we're going to check if the accumulator has more than 5 in it, because if it's more than 5, oh no, we need to do more than or equal to. There's no there's no greater than or equal to instruction in this language, so we need to do something kind of dirty and say greater than, and then say 4. So we want 5, but we're actually going to do 4. And we don't even really have room to comment it. So this may not be great for making programming habits, but you know, we got to do what we got to do when there's this little memory on our device. Okay, so if we do have 5 or more, we're going to turn on the out 5. So we'll move 100, because this is an analog output, onto P1, which is the one that's connected to our 5 dispenser. And then we really want to jump over to, let's see, because we need to pulse it, as you can see here. So that basically means sleeping for 1 and then turning it off, right? Move 0 to P1. I wonder, like this little cleanup routine we can call C. Try to keep these, or, well, let's just do this. Cleanup. We can actually write that all out. And if we get to here, we just immediately jump to cleanup. So that will do a sleep for 1. Can I don't want to make that a line. That's gonna count against my total. And I am running out already. This might have to be a bigger microcontroller, because we want to sleep after that again. This is the trouble. At the beginning, we're sleeping until we get anything, and it's sort of important we don't do that, because we're not going to get a packet every time. Yeah, we're definitely going to have to move to a bigger microcontroller, because we need more lines of code. So I wish, another thing for the developer, I wish you could put this microcontroller on there and copy the code, but you can't. You've actually got to cut and paste it into this one. Okay, and now as you can see, the pinouts are all different, so we have to reroute those. P1 needs to go to out 5, P0 is still going to out 1, x2, we want it to go to x0. Okay, now it's all set up. Yeah, so the trick here is we want that to wait, and then I think we want it to get stuck in sort of a loop here. We want to make some sort of loop. So we'll label this TG if it's greater than, oh yeah. So we'll label this here as dispense, I guess, something like that. And it looks like we can put it on its own line for now. Hopefully we won't run out of space on this slightly bigger microcontroller and more expensive, so we're driving our cost up, but oh well. So dispense, if it's greater than or equal to 5, then we want to give it a 1, and then we wait for a second and we turn it off, and then we sleep for another second, and then we want to go and continue dispensing change. Dispense. So the idea is it would keep doing that. And I guess what we want to do here is also automatically jump to, I wish we could automatically jump to the end, or to the real start. We'll say wait up here. We'll label that, and we'll automatically jump to wait if nothing works. And yeah, we're not going to put these on their same line because we're already running out of space. Okay. Yeah, again, I wish this was more based on instructions as opposed to actual lines, but yeah, whatever. Okay, move. Yeah, so this should handle dispensing 5s just fine. And it doesn't. Oh, maybe it does. Okay, so let's run it. And you can see it gives out a 5, and it continues giving out 5s, and gives out more 5s and more 5s. Okay, so we've just really screwed up here. We want to, whenever we move that, we also want to subtract 5 from the accumulator. So now we only give out 1. But we're keeping three currencies from them, which isn't great either. So we need to also implement dispensing the 1s. So let's do a check here. TGT, well actually, if it's greater than 0, yeah, if it's greater than 0, that means we have some change we're supposed to still give them, right? So we want to move 100 to P0. Oh, we're gonna run out of space. This is bad. This is bad. And we need to sub 1. And we don't have enough room here to turn off the other item. Damn. Because we've already run out of space. Is there a way to jump back to the beginning of the program without actually jump instruction specified label? Well, it wouldn't really make any difference. This isn't taking up any space. So the problem that we're having here obviously is we're trying to do this cleanup operation, and right now we're leaving that on. So it's basically just saying, oh yeah, always keep dispensing 1, and we're never turning it off. And the place to do that would be right down here in our little cleanup routine. But we're out of lines. I think there's probably a better way to organize this, right? Maybe what we don't need to do is ever jump to cleanup, right? Well, no, we need to jump to cleanup so that we don't dispense coins at the same time, because it doesn't want us to. Why doesn't it want us to? I know what we could do. Right now we have to use 2 instructions to turn this off, but if we were using one of these, it would only cost 1 instruction to actually turn it off, because we would be sending 1 value over X bus. So let's move this down here. I want to see it. I want to be able to see all the labels. It's not going to let me. Okay, we'll connect this. We can see the labels here. We'll connect X3 into this bus, and we're not going to worry about P1 is going to become part of these two. This is P0 and this is P1. We may want to do that the other way around because, as you recall, it's sort of backwards. Okay, so now it's freaking out. It's saying, oh, part is not on the board. No, it isn't on the board because it's hitting this little notch. Okay, part connected to self. Is it? Oh, it is. Okay, so you can see sometimes you can get weird wire connections. There we go. Alright, so now it's freaking out because pin 1 is not connected. Let's change this to use X3 instead. So all we need to send to X3 to turn on pin 5 is, oddly enough, 100, because 1 stands for P2 being 100 and the others being off. And then we do the subtraction. This one, since we want to have X3, we want this one to have the middle one on, so we say 0, 1, 0, and then we subtract 1. And down here, when we want to turn them all off, all we have to do is send 0, 0, 0 to X3, and that'll turn everything off. So now, let's run it and see what happens. Okay, so this one gives that change correctly. We can see we have 3 left. Will it turn on and give 1? 1. Oh, it leaves it on. It leaves it on. Dang it. Okay, so I think I see why that's a problem. So you can see this one up here jumps to clean up, but the other one doesn't. It jumps to wait automatically. Oh, also it accidentally automatically subtracts something every time. That's not what we want at all. So what we really want, and that's not even really, well, it is sort of correct. So this is sort of like, we can do like an else, where we only jump to wait. Let's see. This code is getting complicated, and that's one of the interesting and fun weird part. This is code that you would never ever write anything like in real life. I guess some people would, but you would try to avoid it. But that's sort of fun. It lets you you kind of bring out your bad programmer side. And just have this mess of uncommented code that has go-to statements everywhere, all over it. I wonder if we could make this into a class. Yeah, we need to do that. Okay, so let's look at this again. Right now we're having it do this jump over into this cleanup section, which is where it basically sleeps and then turns it off, and that's all great and everything. But it doesn't. It takes up too many lines. So I'm wondering if what we want to do instead, you can see this here, we check if it has 5, and we do our thing here, we turn it on, we take off 5, and then we want it to not get to this line. So right now what we're doing is jumping over it, but what we could do instead, I believe, well, no, that won't work either. I was thinking what we could do here is put a negative, subtract mark, a minus, whatever you want to call it, and then it would run there. But I think so this would keep it from running, but it's never going to change the context, so it's always going to run these lines, I believe. So if we go through here, we step through our code. Oh, I went too far. So if we get to here, you can see it's always kicking out the 1, which isn't what we want. So that doesn't quite work. Let's see. What could we do instead of jumping? Well, we don't need to jump on the other one, do we? Ooh, yeah. So, I mean, this one needs to jump to clean up, right? But this one doesn't have anything to skip over. We just need to make sure not to go to wait, unless we're sure we're done. Which is, I think, going to take another line, because if we put negative here, that's going to work fine for a while. Turns on. Oh, that never turns on. And gets stuck in this cleanup loop. Why would it get stuck in a cleanup loop? Oh, I see. It's just showing it weird. Oops. This is tricky. I wonder if we could use the pulse generator feature that they have on this. There's this undocumented feature that they email you about, where they say basically what you can do is say gen 100. You can say gen on pin x3 a pulse, which I'm assuming would be, again, this is now a problem with this. I don't think it's compatible, because it's going to send 100 or 0, which means it's going to turn on a pin, or it's not going to turn on anything. Which isn't at all what we want. We want it to turn off every pin. All right, let's get back to let's clean some of this up and just take another look at it. Number one, this always jumps to cleanup, which is not what we want. We want it to only jump to cleanup when it gets to when it's successful, right? So we're checking. Let's change this to dis, so it's just like, instead of not so long, stands for dispense. Target. Oh no, test greater than accumulator 4. So if it's more than 4, then we turn it on. And we take 5 away from our change. And again, we don't want to do the other thing. We don't want to actually dispense them both at the same time, which is sort of dumb. But I guess probably makes sense. Maybe the machine doesn't have enough space for all those coins to come out at the same time. So we jump to like a cleanup routine. And then we check. Oh yeah, what's this do? Oh, we check if we have anything else in it. I'm already forgetting what my code does. And we move. We turn this one, and then we turn this one on. And then we take off 1. Alright, so the trick is, fitting all this in, so clean. We'll call this clean instead, just to shorten it up. We're trying to shorten everything up here. Well, we could, and so we've already turned it on, we sleep for 1, we turn everything off, and then we sleep again, I guess. And now we've got 2 lines left. So maybe we just make a line here that says jump to wait if it doesn't work, if there's nothing left, right? Okay, so this is again doing the thing where it doesn't dispense any 1s. Let's see why. So that's sent. It dispenses a 5, we see the 3, and we're going to step through the code. Oh, because it ends up waiting. Right. Right. What if... No, if we wait at the top, it's always going to be a problem, because it's going to take 2 ticks to ever actually trigger anything. So we need to jump to dispense at this point. And that's our last line. Ooh, ooh, that actually works. Okay. Ah, we actually got it to work. Nice. So we jump down. We jump to wait if there's no change left to be given. If there's no ones left to be given. So that could come back to bite us. That's not really great, because what if like what if it was just 5, right? If it's just 5, no, it'll come back and it'll check it again. Yeah, that should be fine. Okay, great. So we've actually finished our little change dispenser microcontroller here. As you can see, down to just the last gosh darned line of code that we can accept. Can't put any more. Okay, so now the only issue that we're running into is if we run it, you can see that it is not turning off a buzzer, which thank God is an easier thing to fix, in my opinion. So what we need to do is, if a buzzer's turned on, if a bell, I guess P1, let's see, where do we turn on P1? Ah, move 100 to P1, and then we subtract. So what we probably want to do is let this whole thing happen, and then if it does, we want to actually sleep for, how long does it want to be on? 1, 2, 3, 4, for 4 seconds. And then we want to turn off our bell. So we'll send 0 over to P1. Okay, let's see what happens. This may block it for too long, but we'll see. Oh, there we go. There we go. It's running. It's running. Oh, okay. So we ran into an issue over here. Let's see. I think let's try to debug this. See what happens. See what happened. So it looks like everything was going fine, and then it goes over here, and the buzzer doesn't go off. Now, why doesn't the buzzer go off? The buzzer doesn't go off. What is the price set to? Looks like it's set to 14. Let's set a breakpoint here. That's one of the things you can do. Control click, and that way when we simulate it, it stops there before it actually goes through that. Okay, keep simulating. Okay, so we've gotten to our breakpoint. You can see that they just put in a 12. Our accumulator is currently at 1. And we're going to step through. We add the 12, and we get 13. Yep. We're checking the price, right? X0? Oh no, X0 is, we're checking to see if anything else is turned on. Okay, so we'll just step through all this. And then we know that the price, it's not enough, according to this. So that's interesting. Maybe we lose track at some point of how much money we have in there, because if we keep running through this, you can see it expects, oh no, here it is. We put in one more coin. Oh, I think I know what this is. I think I know what this is. So we put in this one more coin. We step through it. It recognizes the coin add, and we're now at 14. And then we see if it's greater than X1. So we see if it's more than the price, which is a problem because it needs to be greater than or equal to the price. So when we advance here, it's going to say, no, it's not greater than the price. We can't give them change, so we can't give them the product, which makes no sense. So we can't use the little trick that we did over here where we just put in 4 instead of 5, because when we're trying to see if we have enough money, we're using 2 values that we can't just subtract 1 from. Not easily anyway. No. And we're out of lines of code to do that sort of thing anyway. We could sort of like put it into the DAT register and subtract 1 every time, but we don't really have the lines of code that we need for that because we're out, as you can see. So we sort of have to figure out how to do this in a pretty pretty compact way. Let's see. Are there any lines in here we don't really need? Because we need at least one more line anyway, regardless, right? Like, we're not going to get away with doing this and with no lines. We turn on the buzzer here. What if, I mean, I hate to do this, but what if we have another microcontroller that is just dedicated to turning on the buzzer? I mean, it sounds stupid, and it probably is stupid, but it might give us a little more room to write code. Oops. So let's connect this up with an X bus. Let's sleep until we get code, until we get data on our X0 bus. And then when we do get data on it, so basically all it needs to do, it doesn't have to do this whole routine here where it does the sleep. We can do that up here. So when it gets data on it, what we want to do is just throw it away. So there's a null register you can use, X0 send to null. So that basically just makes it so we're not blocking, which is good because we don't want to be doing that, because the whole thing will just lock up. And then we can turn on P1, so we'll move 100 to P1, and then we'll sleep for 4 seconds. We'll turn it off, and we don't need to sleep again after that, do we? That's just for the other microcontroller. Okay, perfect. So now instead of turning the buzzer on ever, we just move, let's just say a packet of 1 or something like that, over to our X3 bus. So that'll send 1 packet, and then we don't have to do any of this stuff, so we don't have to sleep. Actually, wait a second. We don't have to sleep, we don't have to change it. Yeah, we do have to sleep at the end for this loop. Okay, let's give that a try, see what happens. Yep, there it goes. So it's triggering whenever it's getting a packet, and it's ringing the bell. Oh, but we still run into trouble here. Is this the same place we were having trouble before? Oh yeah, obviously. We moved the code out, we gave ourselves 2 extra lines, but we never actually fixed this problem. Yeah, so we should probably do that. Okay, so TGT ACC X1. So if it's greater than the price, but we also need to check if it's so doing OR statements is a little tricky in this. It's a little tricky, to be honest. How many lines of code do we have left? 1, 2, just 2 lines. Okay. So what we could do is jump in like maybe just a little subroutine instead of having all these pluses there. Yeah. So we could have reset up here. We'll label that. And then if it's not this, so in other words, we'll just like try and jump out to the beginning. Oh no, that's not gonna work. Maybe if we move, because we have to sleep, remember? So maybe if we put, oh no, this is fine. This is fine, hang on. So we'll call it sleep, we'll call the routine sleep, we'll just sleep 1. And we'll just jump immediately to sleep if this fails. And again, I don't think we're gonna have enough space. Ooh, come on. Okay. Oops. It's gonna be tight. Why are we subtracting X1? Oh, because we need to do that before we send it over. And then we move the accumulator X2 and then we send it over. Oh no, this is gonna be tricky. Because we need basically t equal to that, and we need one more we need one more goddamn line. Because we need to jump. We need to jump over to if it fails, right? Oh, hang on. We don't need one more line. We only run this part if that's successful. No, we need an or, not an and. Yeah, we need an or. Wait, if we need an or, then I'm doing this entirely wrong. Okay, hang on. Let's rewind for a second. So we're trying to see if it's greater than or equal to, right? So that's an or, which is interesting to implement in this language. So basically, if either one is true, then we want to do it. which means what we actually want to do is not to have a sleep routine at the end. We want to have, what would this routine be called? Just basically, let's call it or let's call it either. And if this first one is successful, just jump to it. And then, since we don't have any more room to write jump lines, we only turn on this line. Oh no, that's not gonna work because it's gonna jump past. Oh my god, this is crazy. But basically we wanna just, if either of these are true, we wanna go down there. Is there an easier way to do this that I'm like missing? The answer is probably yes. What if we only use, so this is really stupid and probably not a good way to do this. So like we said before, we have this trick where if we just say, oh, greater than or equal to, and we just have it be, we have a value we compare to be one less, then we can get away with it, right? What if instead of ever reading the price at the beginning of every single line of a program, we move x1, which is the price, into the DAT register? Oh no, we can't subtract from it. We can't subtract from the DAT register, can we? No, because it's not. It's an extra. They're initialized. Is there a way? Can we do it? Registers, if arithmetic operations, add value. Oh, I don't think it would let you. Let's just check. Sub 1 from DAT. Could you do that? No, too many operands. Ah. Oh my gosh. Oh my gosh. Okay. I thought I could get away with this, but it is not having any of it. We've done so many crazy things already. I don't know. We need it. ACC. We need that to keep track of stuff. It can't be, and we can't subtract it and then move it into DAT. We don't have room for that. Where do we move stuff into DAT anyway? Did I just delete that line? Did I delete an important line that was supposed to do important things? No, we never move stuff into ACC. That's something we have to use to keep track of. So it wouldn't work anyway. It's not gonna. It wouldn't work anyway. Okay. All right. I see how it is. I see how it is. Game, giving me a hard time. What if we only run this next one if that one fails, right? So we only run this next one if that one fails, right? So t equals to ACC x1. So if this one fails, then it runs this. If this one succeeds, then it runs these lines, right? And if this one fails, it's going to run this, which is going to start a new test statement, which is going to run these if it succeeds. Ooh, this might work. Let's give it a try. And it's more efficient too because it goes quickly. Oh, we left our breakpoint in there. Let's remove that. I wish there was a way to. Oh no! How do I get rid of them? How do I get rid of breakpoints? Because I can't. It runs all the way in here. There we go. There we go. Okay, so yeah, that was a tricky one. But it gives you sort of an idea of how the game works and some of the puzzles that you can expect to be puzzled by, I guess. So this one, it cost a little more than it should have. It's 15, and most people were able to do it. 15. Most people were able to do it for 10. It looks like maybe even 9. Wow, impressive people. And also, I used 32 lines of code. Literally every line of code that I possibly, well, not quite, because I only used some of the lines in the buzzer controller. But that's not great. A lot of people, most people, were able to do it in 21 lines. Yeah, so that's pretty nice. Must be great to be them. Yeah, but that's basically it. You return to your email and they say, oh, hey, look, that works. And you get new assignments. Sandwich assembler. Okay. Well, I'm gonna have to check that out next time. For now, yeah, give it a try. Download it. It's on Steam. And it's a really fun game. I've been, like I said, I've been playing through a bunch of them. It also has solitaire built in. I haven't tried that feature yet. I'm not gonna probably try it anytime soon. But the puzzles are great. Yeah, so I hope you had a good time checking it out, and see you next time.